Hello, my name is Arthur. Thank you for attending my presentation on the use of thrusters on bipedal gait design. This work aims to contribute to multimodal locomotion control design, which is the ability of not only moving through different types of terrains, but also leveraging the actuator from one mode of locomotion into another. And specifically in this work, we will focus on the synergy between terrestrial and aerial locomotion motivated by the RP, the hybrid land-air bipedal robot being developed at the Silicon Synapse laboratory here at Northeastern University. As you can see in the picture, Harpy has not only a pair of legs for bipedal locomotion, but also two thrusters that have both their magnitude and direction controlled. In this work, we will study how the thrusters can aid in the design of a bipedal walking gait. We begin our presentation with a brief overview of the hybrid aerodynamics framework, which will serve as our foundations. Equation 1 presents the equations of motion of the robot, with QB being the body coordinates and Qn the absolute one. U is the vector of the joint torques and Ft is the vector of the thruster forces. By computing U as in equation 2, we can write the closed loop system as in equation 3, where sigma n is the angular momentum of the system about the world frame. We can now write the outputs of the system as in equation 4, where Ht is the virtual constraints or the joint trajectories of the system. Choosing the gait timing variable alpha such that alpha and y are a diffeomorphism of the system allows us to compute the feedback linearization control law that enforces the virtual constraints exponentially, as in 6, and renders the aerodynamics forward invariant as in 7. With this, we are ready to begin to study the effects of the thrusters in the gait design process. The first question we aim to answer is how the thrusters can influence the existence of the limit cycle and which constraints we need to consider when in its dynamics. In order to do that, let's consider that for some values of the thruster influence on the aerodynamics, that is BNFT, the system has a stable limit cycle. This can be interpreted for the robot as a thruster pushing or pulling the robot with a constant force, and intuitively, we would expect that for any forward push and for sufficiently small backward pulls, we would never result in a failed gait. And as such, we suppose that there is a continuous interval C of the system of real numbers, where for any constant value of BNFT on that interval, the system still has a stable limit cycle. If that's true, and that can be easily verified from the solution of the Poincare function of the aerodynamics, then for any constant value of the thrusters in that interval, Theorem 4 of Manchester and Slotin's papers assures us that such system is transverse contractive, and Theorem 5 of the same paper tells us that if a strongly contractive system x1 dot equals f of x1 and a system x2 dot f of x2 is transverse contractive if x1 is viewed as a constant parameter are cascaded together, then the resulting composed system is also transverse contracting and has a unique stable limit cycle. This result gives us conditions for the dynamics of the thrusters. And to illustrate this result, we present some simulations with a simple three-link bipedal robot where the thrusters are considered as a second-order linear system with dynamics comparable to that of the robot. As you can see, for strictly negative steady-state values of this thruster, the limit cycle flattens out and gets quicker, which would be the expected behavior if we are pushing the robot forward. Despite such a result, it is also true that usually the thrusters converge to the steady state much quicker than the robot takes to take a step. Unless we're studying particularly agile movements like jumping and running in particularly small robots that have quicker dynamics, the hypothesis that the thrusters are piecewise constants along the step is a reasonable one, which motivated the study of how the thrusters can shape the resulting limit cycle when viewed as an instantaneous changing parameter of the system. First, let's consider that the effect of the thrusters in the aerodynamics is constant during the whole step. The solution of the Poincare function of the aerodynamics can be written as in equation 11, where zeta comes from this change of variables. By defining in 11 zeta 0 as a nominal solution of the aerodynamics, that is, the solution with no thruster influence, and Bf as the equation in 13, we can rewrite equation 11 into equation 14 for convenience. And now let's take a look at the limit cycles resulting from constant values of the thruster magnitude. They are very similar to the results from considering a second-order dynamics for the thrusters, except they are slightly farther apart since the instantaneous converge to the steady-state value. While the thrusters are clearly flat in the limit cycle by changing its shape, this is somewhat limiting since, for example, the robot presents faster velocities at impact the more you shape the limit cycle, which might, for example, damage gearbox and motors. To circumvent this problem, we look at the instantaneous changes to the thruster magnitude during this step. As an example, consider a single change in the thruster value from T1 to T2 at the instant alpha 1. The solution of the Buckeye function becomes as in equation 15, where each of the magnitude values is weighted by the function bf. Generally speaking, equation 16 gives us the solution of the Buckeye function for n-1 instantaneous transitions during the step. With this, we can, for example, design a gait with two instantaneous change to the thruster values in a way so that the robot moves faster, but the pre-impact velocities are the same, which results in a faster walking gait overall while preserving the robot's components. While this is the main result we were looking for in the paper, there is one remaining question that we need to answer, and it is how the thrusters affect the compliance with the unilateral contact forces constraints, both during the impact and during the continuous phase. To answer that, let's first consider the thruster effect in the impact. Integrating the unpinned model from equation 17 during the instant of the impact and adding constraints for no slippage and rebound of the swing leg gets us the system in equation 18. We can then compute F2 from 18 as in 19, which after being restricted to the zero dynamics has the form of 20. Notice now that during a step, the angular momentum about the world frame sigma n is assumed to have a constant signal. Otherwise, the robot will start moving backwards during the step. And also notice that the horizontal and vertical components of the impact forces can be written as a nonlinear function of the pre-impact value of the gait timing variable, which is invariant under thruster influence, and then multiplied by the pre-impact value of the angular momentum. And notice now that if for the nominal gait, the no rebound condition, that is the vertical term of F2 is greater than 0, is satisfied, then it will be satisfied for any constant value of the thrusters that result in a successful step, since sigma n has a constant signal. And similarly, if the no slippage condition is satisfied for the nominal gait, it will always be satisfied for any thruster value, since sigma n is cut out from the ratio. And so the thrusters do not influence the compliance with the impact force constraints. Looking at the contact forces during the continuous phase, we consider again the unpinned model in equation 21, which can be written as in state space form as in equation 22, where Fr is the resulting force from the contacts and the thrusters, and it can be computed from equation 23, which is then written as equation 24 once restricted to the zero dynamics. Again, notice that the complex nonlinear terms are all functions of alpha and invariant under thruster actuation. As such, those functions can be approximated by polynomials or even simpler nonlinear functions offline and then be used to build an optimal controller that computes both magnitude and direction of the thrusters and that give the desired influence over the zero dynamics B and Ft while still complying with the approximated ground contact constraints in equation 25. So to recap the results presented in this paper, we first studied under which conditions the existence of the limit cycle is affected by the thrusters. And then after that, we successfully proposed a framework that can be used to shape the limit cycle based on infinite instantaneous transitions for the thrusters. And finally, we showed how this can be accomplished while still complying with the unilateral ground contact forces constraints. Thank you very much for your time and attention, and I'm open to any questions.